Hello everybody, here is your final Calculus BC video. It is on polar area. We're going to start with the area with one polar graph, and then we're going to go on to the area between two polar curves. So I want to briefly remind you about the difference between area under a function in the Cartesian xy plane, where we split it up, or split up the total area from A to, let's say, B into infinitely many rectangles, and added up all those rectangle areas to approximate the actual area under the curve. If we're in polar, we don't have an A and B left and right. We're going to have a theta 1 and a theta 2. Keep in mind, theta 1 is this rotation, and theta 2 is that rotation. So in polar, we're not really finding the area under the curve. We're finding the area bounded by our two angles, theta 1 and theta 2, the amount of rotation, and also bounded by my actual function r equals f of theta. So don't think under curve, think spinning around in a circle or going up a spiral staircase, and visualize it like that. Now in polar, the trickiest part is finding your bounds, theta 1 and theta 2. I mean, you're always going to use the same function, 1/2, or the same formula, 1/2 r squared d theta. Finding these limits is crucial. Amount of time on the video helping you find the theta 1 and theta 2 to help you set up the area between, or the area for a polar graph. Write down this formula here. We'll be using that in the second half of the video. And this is if I have two functions and I'm finding the area between the two polar functions. In that case, theta 1 and theta 2 will often be intersection points. In AP free responses, they're usually going to have two polar functions, and you'll find the area between them. Sometimes they give you theta 1 and theta 2. If not, you just set r1 equal to r2 and solve for theta. All right, so let's go ahead and actually try one. We're going to try a more basic one, and then we're going to work our way up to the AP level ones. You're not quite at the AP level ones yet. I want to do this one, r equals 6 cosine of 3 theta. Keep in mind, this is in the setup of a rose curve. We're going to have 3 petals, because that's the coefficient here, n, in front of theta. And this 6 up front, that coefficient, tells you the length of each petal. Now, keep in mind that on the AP exam, you're not actually going to have to draw polar curves, so you shouldn't be worrying about spending half an hour actually drawing this. They are going to usually give you the graph here, and I'm going to graph it quick, and then we can continue from there. Draw that on your notebook paper. If you don't have a polar grid, then just do your best to sketch it. Keep in mind on my grid, it goes 15, 30, 45, 60, 75, 90. I don't want you to get confused whenever you're following along with what I'm doing here. So what I really want is the area of one petal here, and that one petal would basically be this right here. Oftentimes in polar, whenever you do this, you're not going to actually do one whole petal like this. It's usually strategic to maybe find half a petal or part of a petal and use multiplication to get everything that you want. Now, since we didn't actually plot this by hand and take the time to see exactly where I started, where I am in the middle, and where I end up, what I usually do, just to get my bearings and see like where I'm actually starting and where I'm plotting, I want to find where I am when theta equals 0. That's basically where you're going to start the whole graph if theta is 0, because remember we used to plot these on the Cartesian plane, theta r, and we basically want to know like where do I start on the left. So what I'm going to do is solve for r and plug in theta. So I'm going to do 6 cosine of 3 times 0. So r would be 6 cosine of 0, and cosine of 0 is 1. So I'm at 6. So whenever r is 0 and theta, whenever theta is 0 and r is 6, we're going to start right here. That's my starting point. Now my graph is going to go like this, remember, counterclockwise, and I'm going to eventually hit the pole. And it's not like next I would go here. Where you're going to go next is actually down here, and then around, and finally here. So I'm not going to get to the bottom portion here, which I'm really interested in, until the very end. So that's a problem for me here. So to avoid that problem, what I'm going to do is actually just find, because I'm going to start whenever theta is 0 here. I'm going to move this way, and I'm going to end up at my pole at some point. I need to know where I am when I hit the pole, and that will be my second bound on my integral. At the pole, keep in mind that r equals 0. So what I can do to find where I am when I hit the pole is to find when r equals 0. And if you didn't jot these two things down, jot them down now, because that's going to be a huge guideline whenever you're trying to figure out how your polar graph works. I'm going to take my function, 6 cosine of 3 theta, and I'm going to replace r with 0. And let's just solve for theta here. So if you divide by 6, you have cosine of 3 theta. I need to get rid of theta, so do cosine inverse of 0 equals 3 theta. Okay, on my unit circle, I want to know whenever cosine is 0. That would be here and here. So I have pi over 2 and 3 pi over 2. That equals 3 theta. In order to get theta alone, let's divide by 3. So then theta would be, what is that, pi over 6 and pi over 3 pi over 2 divided by 3 would just be pi over 2. Okay, which of these do I actually care about? You have to remember, you start here whenever theta is 0. Right here, whenever you plot on the trig plane like that. I go in a counterclockwise direction, and I stop and I hit the pole here. What I'm interested in order to get this little bit here, is the first time that I hit the pole. So this is the first time we hit the pole. And pi over 2, it might hit the pole again whenever I'm at pi over 2, like here, and it'll actually hit the pole again here, but I don't care about those two because this has nothing to do with my yellow piece right here. And actually, whenever I solve this and I said pi over 2 and 3 pi over 2, so pi over 2 and 3 pi over 2, there's actually another one, and it would be 5 pi over 2. So if I had done 5 pi over 2, that would have given me a third angle. So 1, 2, 3. I hit the pole 3 times and I want the first time. So that's going to be my pi over 6. So you have to decide which one of these do you want, and that all is going to depend on your graph. So let's actually plug into our formula here. So I'm going to have 1/2 times the integral of 6 cosine of 3 theta squared d theta. That's the easy part, just copying down r. I start whenever my theta is 0. This is the first angle boundary that I want. I let myself rotate pi over 6 until I'm at the pole again. So I'm going to stop there. Now keep in mind, I really want this whole area. And what I just wrote down is only going to give me the area of half of that. So all you have to do is multiply by 2, and you'll be good to go. Calculator, you do not need to be in polar mode. You can just be in function mode, and wherever there's a theta, just put x and understand that it really is theta. And to 3 decimal places, you should get this as your area of this piece right here. Let's try another one. Now keep in mind what I'm doing. These are examples on the half sheet I gave you. I give you a half sheet of, I believe, 6 area basic practice problems. I'm going to do number 2 with you also, and then hopefully you'll be all good to go to do 3, 4, 5, and 6. That was part of your homework in addition to the take-home tests. Okay, so I want the area of one petal. Once again, I only want one petal of 3 sine of 2 theta. Once again, I'm going to have a rose here. I'm going to have 4 petals. And let's see here. Again, we're not too concerned with the graph. I'm going to give you the graph in just a second. You're going to connect it like this. The petals have a length of 3. And they're all symmetric here. Okay, so I want 1 petal. So pretend that you were just given this graph here and you didn't watch it get graphed, so you don't know where it starts or ends. Again, what we want to know is where do I start and where do I hit the pole again. So we're going to go through those steps again here. So where do we start? Make sure you have this sketched first before you continue. I want to know when theta equals 0, when I've just started my graph, where am I? So I'm going to do r equals 3 sine of 2 times 0. Well, sine of 0 is 0, so r is 0. And that makes sense because we started right here at the pole. And I want, now when we graph it, we're going to go counterclockwise, so this way. Counterclockwise, counterclockwise. In this case, it doesn't really make sense to split my petal in half because my rotation is continuous and uninterrupted up until I enclose that 1 petal. It's important to realize that up here, my 1 petal was interrupted by all of this stuff over here until I enclose that petal. Down here, my 1 petal is contained real nicely from where I start until I hit the pole right here. So if I just find the first time I hit my pole again, I've completely contained this one polar petal here. So 2, we want to hit the polar in the middle. So I'm going to let r equal 0 because right here the radius is 0. So 0 equals 3 sine of 2 theta. Let's solve for theta and see what happens. Divide by 3. I'm going to need to sine inverse this to undo sine on the right-hand side. All right, where is sine 0? Here and here. That will be when theta is 0, pi, 2 pi, etc. You could keep going. Again, I only want the first time this happens, so I'm not going to keep going forever. Divide by 2, and theta is 0, pi over 2, pi, etc. Now, this theta of 0 represents when you first start graphing. You're at theta 0, r 0. Pi over 2 represents the first time you hit the pole. Pi would represent the second time, and you could keep going. We only care about this one right here. So we have it. So we're going to have 1/2 r squared d theta. I start when theta 1 is 0. That's where I start rotating. I want to stop my rotation at pi over 2 the first time that I hit the pole. And when you type that into your calculator, which you should practice typing into, just to make sure that you can actually do this, you get 3.534 rounded. Go ahead and do the other problems on your half sheet. Do these. The emphasis is not on drawing them by hand. The emphasis is on setting up the area formula and figuring out your bounds. So go and decimal to your graphing calculator and just sketch the graph and shade in what you're trying to find. And then focus on this and this. So I want to see work for both of those. And then you can use your graphing calculator to actually get a value. Okay, let's try our first free response here. I think you all are ready for this. I love this free response because there's 2 different ways to solve it. And once you understand both ways, you'll have a really strong understanding of how polar area actually works. So I have polar graphs r equals 2, which is, remember, the circle. And we have 3 plus 2 cosine of theta, which is this cardioid / limacon looking graph. And what we want is, first of all, they give us the intersection points, 2 pi over 3 and 4 pi over 3. So here's 2 pi over 3. And here's a 4 pi over 3. So in this case, you didn't actually have to find them. They just found them for you. And we're going to let region R be the region inside the graph of r equals 2. So inside of this circle. And also inside of this polar graph. And the area that's shared by both of them is the area that they actually shaded on the free response. So our job is to find the area of the shaded region. Now there are 2 ways of doing this. Using this formula here, which is going to give us the area between 2 polar graphs. The other way is going to involve breaking our area up into 2 regions and summing the areas. Now a really important thing to keep in mind is that I have my blue curve and my green curve. The area between the 2 curves is not the region R. The area between the 2 curves is actually this, shaded in yellow. So take a minute and picture. I have green and I have blue. In between them is this. This is the exact opposite of what I want. So notice we would have the area of an entire circle here, which is really easy to find. And then the area between the 2 curves gives me the stuff I don't want. So how would I get the stuff I do want? We're going to revisit that in just a moment. Before we actually do it out, I really want to point out what each of these 2 different things really means. So let me go back to my little sketches here. These 2 sketches right here. And I will actually give you the free response whenever I see you in class again. But visually, whenever I have this right here, the integral from 2 pi over 3 to 4 pi over 3 of this r, what I have is, so I'm going to start rotating, and I'm going to rotate until I get to 2 pi over 3 right here. I'm including all the area up until I stop rotating at 4 pi over 3. So this chunk of the circle right there. Visually, if I have this graph where I start when theta is 0, I'm rotating, oh, there's 2 pi over 3. and then it's all this area all the way until, whoop, 4 pi over 3. So visually, those are the two.